Welcome to Math with Professor V. In today's video, we're diving into optimization, one of my favorite applications in calculus. Honestly, it gets hated all too often. Now, this is a continuation of my earlier optimization video lecture. So if you're revisiting the topic or learning it for the first time, this one's for you. I'll link those previous videos in the description box as well. It's perfect for Calc 1 students or anyone studying AP Calc AB or BC. We're going to work through 3 classic examples step by step so you can really see how to set them up. That's honestly the hardest part for students. How to take all your derivatives and then interpret what those critical points mean. So here's the strategy. First, read the problem carefully. I'd say honestly read it once really fast and then carefully. Then draw a diagram whenever possible. Let's be honest, it gets awkward when you stare at a problem and don't write anything down for too long. So just draw something. And then the third thing that's important is you need to introduce notation. So we're going to start labeling the picture, labeling what things represent, introducing variables into our problem. Now here's the key. Express the quantity to be optimized in terms of the other variable. There's always going to be a keyword like find the max volume or the shortest distance. So that's the quantity that you need to set up an equation for in terms of the other variables. And then we have to reduce the number of variables in equation 4 to only 1, meaning you got to write the quantity you're optimizing as a function of one variable. You're still just in Calc 1. We're not dealing with multivariable functions. And then after that, you find the absolute min or max. So you take your derivative, find your critical values, etc. That part, you're pretty much home free as long as your calc skills are on point. So let's go through some examples. I'm going to do like the classic 3. And then if you guys want a continuation, I got plenty for you, so we could do that too. Okay, here we go. From a thin piece of cardboard, 50 inches by 50 inches, square corners are cut out so the sides can be folded up to make a box. What dimensions will yield a box of max volume? What is the max volume? Round to the nearest tenth if necessary. Okay, so we have a thin piece of cardboard. It's 50 inches by 50 inches. And what do we do to it? We cut little squares in the corners and fold the sides up to make a box. Have you ever done this? I used to do it. I used to make little beds for my dollies out of this or whatever. So this gets cut. This gets cut. This gets cut. They're all the same size. And this gets cut. So imagine those are erased. Those are erased or removed, and you're just left with this shape here. And then what happens is you can fold the sides up and you have a box. Yes. And then, you're a kid at home, you got a little bit of tape, you're good to go. I mean, you have made yourself a snazzy little box. Okay, so while I color it in, let's reread the question. So they want to know what dimensions will yield a box of max volume. Okay, so in order to set that up, what I need to do is introduce some notation because I'm going to try to figure out what's the volume of this box here. You guys just let me color, okay? Let me do my thing. It's therapeutic. Okay, perfect. So it's going to be a box, right? So we know how to find the volume of a box. The volume is equal to length times width times height. Now, I don't know how big of a square we're cutting out. That's really what the crux of the problem is. So we need to determine that. Since I don't know how long or how big each of these squares are, I'm going to label this side X, okay? The side of the square. Pretend they're all the same. I know that one looks a little big down there. It's fine. Don't worry about it. Okay, so I'm trying to figure out the volume. Now, what would be the length of this box? The length would be this side here, right? Because you got to imagine this all gets folded up. So this is the length from here to here. How much is that? Well, originally this whole side was 50 and then minus an x minus an x. So that side is 50 minus 2x. So length is 50 minus 2x. What about the width? Oh, it's the same, isn't it? Yeah, because this was a square to start with. So that would also be 50 minus 2x. And then what's the height? Well, imagine these all get folded up. So how tall is the box? It's x. That's how tall it is. So that's the height. Okay, so we've not only introduced notation, now I have volume as a function of x, and let's clean it up. It's x times 50 minus 2x squared. This is the quantity that I want to maximize. I want to maximize the volume. So how do we do that? Well, we're in calculus, so we know the maxima occur where we have critical values. So we need to find critical values, meaning I need to take the derivative and set it equal to 0. Okay, let's multiply this out. It'll be easier than just doing a bunch of chain rule nastiness, I think. So v of x is going to equal x times, I'm going to square all of this. So square the first term, it'll be 2,500 minus 2 times 50 times 2x, so that would be, very good, 200x, plus square the last term, 4x squared. And then distribute that x, so v of x is 2,500x minus 200x squared plus 4x cubed. Good? Okay, so now we're on a hunt for critical values, so we need to take the derivative. So v prime of x, good thing they gave us a relaxing polynomial. 2,500 minus 400x plus 12x squared. Critical values come from where the derivative equals 0 and where it doesn't exist. This is just a polynomial, so it's going to exist everywhere. I just want to find its zeros. So let me set this equal to 0. And let's put it in descending power so it's a little easier to work with. 12x squared minus 400x plus 2,500 is 0. Ooh, do you see? We can divide everybody. We can divide everybody by 4. Okay, perfect. Then we have 3x squared minus 100x plus, 625 is 0. Okay, this will factor 3x, x, and then 625 is 25 times 25. So 25, 25, these would both have to be negative. Perfect. So from here I get either x is 25 over 3 or x is 25. Are those both viable? Because remember, the box, or it comes from a thin piece of cardboard that's 50 by 50. 25 over 3 would make sense, but 25 wouldn't, because if each of these x's is 25, and then I have 50 inches to start with, I wouldn't even have a little bed to make for my dolly after. That's cutting too much. There would be no box. So this one we're actually going to throw away because it's not valid in the context of the problem that we're doing. So you always got to be on the lookout for that. Okay, so here's my one and only critical value. What do I need to do next? I need to verify that this indeed yields the max volume. And you have two options. You could either do first derivative test with the number line, which is fine and dandy. Or what's really nice on most optimization problems is to do the second derivative test. So let me remind you how it works. You take the second derivative of the function you're optimizing. So in this case, I already have v prime. I'm just going to take one more derivative. So v double prime of x would be negative 400 plus 24x. I substitute in my critical value, which is 25 over 3, and I want to check whether or not this is going to be positive or negative. So negative 400 plus 24 times 25 over 3, this is going to be negative 200. So why is that important or useful? Well, remember the second derivative tells us about the concavity of our graph. So if the second derivative is negative, that means our graph is concave down at this point, at 25 over 3. And I also know 25 over 3 is where the first derivative was equal to 0, exactly. So if the first derivative is equal to 0, that means our tangent line is horizontal. And if the graph is concave down there, then the only way for that to be true is if we have a max at that point, at that critical value. Perfect. So from here, we can say, all right, we know 25 over 3 is a critical value that yields the max. And then let's make sure we go back and answer the question. They wanted the dimension. So they want length, width, height that will maximize the volume. So we know since we got x was 25 over 3, that's the height. And then the length and the width are going to be 50 minus 2 times that. So that's fine. Let's just add that in there. So the length and the width are the same. 50 minus 2 times 25 over 3. So that's 50 minus 50 over 3, which is 150 minus 50 over 3, which is 100 over 3. So I'll put units in now. So the dimensions, let's just box our final answer over here. Dimensions would be 100 over 3 inches by 100 over 3 inches by the height is only 25 over 3 inches. And no one asked for the volume, but you could give it to them if you wanted. I don't know, or maybe do less, just so you don't accidentally mess it up. Oh no, it did say what is the max volume. Oh my God. Okay, we have to focus then. So the max volume, 100 times 100 times 25. Okay, we got that. 250,000 divided by 27 inches cubed. Oh my God, please read the problem carefully. Don't get too excited like I did. I was so ready to do the next one. I love the next one. Okay, are we ready? All right, good. Now looking at this next one, you should get excited. Not only did they give you a diagram, they labeled it for you. I mean, someone is taking mercy on your poor soul. Okay, a rectangular sheet of perimeter 27 centimeters. That means all the way around here. So 27 centimeters. Dimensions x centimeters by y centimeters is to be rolled into a cylinder as shown in part A of the figure. Roll her up. Roll her up. What values of x and y give the largest volume? Volume. So that's the quantity that we're trying to maximize. Good. So we want to maximize volume of a cylinder. Do you know the formula for volume of a cylinder? If you don't remember, I'll help you. When you find volume and you have a right 3D solid, meaning the height is perpendicular to the base, you take area of the base. Well, what sort of shape is that? That's a circle, pi r squared, times the height. Okay? Great, we've got an equation on our paper. Now I gotta focus, make sure I get this as a function of one variable. Notice they told me, oh, this height here is called y. That's the height of the cylinder. So let's go ahead and replace that. V equals pi r squared times y. And then there must be some other piece of info I'm not using that will allow me to eliminate the variables in the problem. And I haven't used the fact that the sheet has perimeter 27 centimeters. So let's see how that's gonna clear things up for us. Perimeter is the sum of the lengths of all of the sides. So this side up here that's not labeled, we know that that's gonna be x also, and this is gonna be y also, right? So that means 2x plus 2y is equal to 27. Okay, that looks interesting. And then there's one other thing I haven't used as well, and this one's the sneaky part. Notice this length x becomes the circumference of the base. I say circumference because it's a circle. And that's how I'm going to relate the radius to x. We know the circumference of a circle is equal to what? 2 pi r. And in this case, I know 2 pi r has to be equal to x because that's the paper that I rolled up to make the cylinder. So x is equal to 2 pi r. So it looks like what we're actually going to be doing is making volume a function of x, because I can find the radius in terms of x, and I can also find y in terms of x. No other combo is going to work. So let's go ahead and do that. So r equals x over 2 pi. And then over here, if I want y, 2y is 27 minus 2x. So y is 27 over 2 minus x. How do we feel? Okay, this one had a lot of parts to it to get the volume function all together, but it's manageable, okay? It's manageable. So now we can say volume is a function of x. It equals pi times, instead of r, you're going to replace it with x over 2 pi squared. And then instead of y, you're going to write 27 over 2 minus x. Oh, I should have scooted the 27 up a wee bit more. There we go. All right, how are we? We're surviving. Okay, clean it up. We're going to have to take a derivative, and right now it's really grossing me out. So we have v of x equals pi times x squared over 4 pi squared times 27 over 2 minus x. And then, see, a pi is going to cancel. Okay, I feel better already. And then we could just put 1 over 4 pi as a constant in the front. 1 over 4 pi. And then, you know what we're going to do? We're going to distribute this x squared inside. Because why do product rule if you don't have to? So this will be 27 over 2. See, I'm thinking ahead. I'm like, I'm going to take a derivative in a hot second. Let me set myself up so it's not so bad to do that. Okay, now look at what we just did. Look at how nice life is going to be. I put the constant all the way out here. So when you take the derivative, you just ignore it, right? It's just going to come along for the ride. You only do product rule if you have variables times variables. So constants, just bring them down, and then we can just take the derivative of this very relaxing polynomial. Okay, here we go. Ready? It's critical value time. We're going to get our critical values. Let's box this guy, though. This is our nice volume function. Yes. Okay, so v prime of x is going to be, leave the 1 over 4 pi alone. Okay, derivative of 27 over 2x squared, derivative of x squared is 2x, so the 2 will cancel. So I have 27x minus 3x squared. Very good. This derivative will never be undefined, so I'm just going to set it equal to 0 to find my critical values. So now I can just ignore the 1 over 4 pi and focus on when 27x minus 3x squared is 0. I can factor out a 3x, and then I have 9 minus x equaling 0. And then from here, well, let's see. X can be 0 or x can be 9. How do you feel about that? Well, let's see. Does it make sense for x to be 0? No. If x is 0, I won't even have a cylinder. I wouldn't be maximizing the volume. So throw that one away. You make no sense. Could x be 9? Possibly. Okay. So now what I want to do is verify that x equals 9 yields the max volume. And we'll do the second derivative test again. So you're going to find v double prime. So just go up here. 1 over 4 pi just comes along for the ride. Okay, 1 over 4 pi. Derivative of 27x, 27. Derivative of 3x squared, 6x. Very good. Then I'm going to substitute in 9. So 1 over 4 pi, 27 minus 54. I honestly don't care what it is. No, we don't. All I care is that it's negative, which means my graph is concave down at that critical point where the tangent is horizontal, because the critical point came from where the derivative is 0. So yes, it indeed yields a max. Perfect. And then the problem asks for us to give the values of x and y that yield the largest volume. So we'll say x has to be 9 centimeters, right? That's what we just got. And then y, how is y related to x? We have it right here. Did you forget? It's okay. So y equals 27 over 2 minus 9, which is 18 over 2. So this is going to be 9 over 2. So y is 9 over 2 centimeters. And this time, no, they didn't ask for the volume. I just double checked. That's all they needed. Good? Okay, I got one more for you. A rectangular field is to be enclosed on 4 sides with a fence. Fencing costs $5 per foot for 2 opposite sides and $7 per foot for the other 2 sides. Find the dimensions of the field of area 870 feet squared that would be the cheapest to enclose. Okay, so here's where your reading comprehension skills have to be on full blast. I know they mentioned area, but what quantity are we trying to optimize? That word cheapest is it. Cheapest means you're trying to minimize the cost. Yep. The area is just there as an extra piece of info. No, not to confuse you, because we're going to need it to reduce the number of variables in our equation. Okay? So here we go. we need to fence this thing. It's $5 a foot for two opposite sides and $7 a foot for the other two sides. So whatever, just label it however you want. I'll call this X, I'll call this Y, and then I'll just say the Y side is $5 and the X side is $7 a foot, okay? So how would you find the cost for all the fencing? Well, I have X feet here to fence, X feet here to fence, so I have 2X feet, and then they cost $7 each foot. So the cost would be 2X times $7 plus, and then for the other sides, Y, so 2Y, and those are $5 a foot. So 2Y times 5. So my total cost would be 14X plus 10Y. And see, we're only in Calc 1. We don't know how to take derivatives if there's more than one variable in the function. So this is where we need to use the area info that they gave me so I can reduce how many variables are in the problem. But the problem doesn't have anything to do with maximizing area. That's more a constraint given to us. Okay, so we know the area, which is going to equal X times Y, has to equal 870. So basically, it'll be equally easy if you solve for Y or solve for X and put it back in here. So it's really up to you. You could do it either way. I'll just solve for Y. That way we have a function of X because that's probably what you're more used to. But you could feel free to switch it up. Maybe you're sick of X's. I get that. So Y is 870 over X. I'm going to replace that right in there. And then now I can write C is a function of X, right? I don't have to keep writing cost. Do you notice I wrote cost here because I had two variables, cost here because I had two variables. Later, when you're in multivariable calculus, you could write C is a function of X and Y, but we're not doing that yet, okay? We're not doing that yet. So we'll have 14X plus 10 times 870 over X, okay? And then you got to think to yourself, what's coming? Set yourself up for success. I'm going to have to take a derivative. So let's make it as easy as possible to do that. 14X plus, this is 8,700, X to the negative first. Oh, much better, much better. Okay, here's our cost function. I want to minimize this guy. So let's go find the critical values. Let's take a derivative. C prime of X is going to be 14. Derivative of 8,700 X to the negative first would be negative 8,700 X to the negative second. Very good. Okay, if you rewrote this, this is 14 minus 8,700 over X squared. Now, critical values come from where the derivative is 0 and where the derivative doesn't exist. This doesn't exist if X is 0, but that's really not in the domain of the problem because then we wouldn't even have a field. So you don't have to worry about that being a relevant critical value. I'm just going to go ahead, set this guy equal to 0. So then I have 14 equals 8,700 over X squared. So X squared equals 8,700 over 14. Okay. And then X is going to be not plus or minus, just the positive square root of 8,700 over 14. And I'll go ahead and just round this to about 24.9 feet. Okay. Now, I don't know for sure that this yields the min cost. I need to verify. Don't forget to do this. So what are we going to do? We're going to take a second derivative. So here's my first derivative. I just need one more. So C double prime of X, derivative of 14 is going to be 0. This derivative, bring down the negative 2. So now it's going to be positive 2 times 8,700 X to the negative third. And remember, I told you you don't really care what it is. So this is 2 times 8,700 over X cubed. If I take C double prime and I plug in 24.9 for X, right? 2 times 8,700 over 24.9 cubed. I don't care what that comes out to. I can tell it's positive. If my second derivative is positive, that means my graph is concave up. Very good. Concave up. And the critical value is where the derivative was 0, meaning horizontal tangent. So the only way for that to happen, if your graph is concave up and the tangent line at that point is horizontal, is if you're at a minimum. Local min. Why am I writing min so ugly? Okay, min. Good? Okay, so we know x equaling 24.9 indeed yields a min. So 24.9, like we came up with x and y in this problem. So you can't give your answer, here's x, here's y. Nobody is interested in that. You have to answer the general question since they didn't give you the variables. So that means $7 a foot is at 24.9 feet of fencing. So 24.9 feet at $7 a foot. And then y, how do I find y? It's 870 divided by x. So it's going to be 870 divided by, if you're putting it in your calculator, put it in with the unrounded version, like do 8,700 over 14 square root and then 870 divided by that. So it's about 34.9 feet at $5 a foot. So they just wanted the dimensions. So really, you know, you have 2 times this and 2 times this that make up the perimeter, right? Okay, good. But they just want the dimensions. So it needs to be 24.9 by 34.9. These are the dimensions. And then you give the cost for each of them because we came up with x and y. And obviously, it makes sense. The more expensive side, we do less of. Boom. Okay, how was that one? Spicy? If you found this video helpful, check out the rest of my AP Calculus and Calc 1 video lecture playlists for full lessons, examples, and practice problems. And you guys, if you want to see part 2 on optimization with some trickier or spicier problems, let me know in the comments. I love hearing what topics you want next. Don't forget to like, subscribe, and share this video with a classmate who's currently suffering through word problems. They'll thank you later. And you can also follow me on Instagram and TikTok, Math with Professor V.